This video is going to cover tests of standard deviation. So let's go look at the standard deviation test problems. And let's go to the top for the first problem. The fine tool company claims that the standard deviation of the diameter of their 20 millimeter sprocket is 10 micrometers. A sample of 21 sprockets yields a standard deviation of 13 micrometers. Test that the alpha equals 0.05 significance level that fine tools claim is true. You'll notice that I've highlighted in yellow the claim information because it says test at a certain significance level, in this case 0.05, so we know alpha, that their claim is true, and here's the claim: standard deviation is 10 micrometers. So we know it's sigma equals 10 micrometers, or sigma equals 10. So we have our alpha, we have our claim. The null hypothesis is going to be the same, is going to be always equal. So the same parameter, sigma equals 10. And this is the value we would use for any assumed value. Anytime we see sigma in the test statistic, this is the number we're going to be using. The alternate depends upon what the claim is. Since the claim has equality in it, then the alternate is going to be the complement of that, which is not equal. So the alternate is not sigma not equal 10, making it a two-tailed test, which becomes important as we go through the steps of the hypothesis test. The test statistic is a chi-squared test statistic, and it requires that we know the sample size n and sample standard deviation s, as well as the assumed value of sigma. Well, we know the assumed value of sigma from H0. It's going to be 10. N and S have to come from the problem, the sample information in the problem, and I've highlighted that in the problem. And we have 21 sprockets and a standard deviation of 13. Therefore, this 21 is the sample size, N, and 13 is the sample standard deviation, S. So we've got that. And we also know that the standard deviation test statistic, chi-squared, has, as a distribution, has degrees of freedom, the sample size minus 1. It's the same degrees of freedom as we had for test of the mean. And that will become important as we go farther on here. Okay, so now in step 3, then what we're going to do is, since we got a test statistic value of 33.8 in step 2, we need to know if this is an unlikely value or if it is not unlikely, okay? So the critical values, in this case, since it's a two-tailed test, we need 2 of them, one on the left and one on the right. We're going to use table A4 to get those. And here are the instructions for table A4. For a left-tailed test, well, let's look at see what table A4 looks like. So I'm going to stop sharing that and go find table A4. There. And this is what table A4 looks like. It's different from the other tables. It has critical values in the body of the table. And across the top, we've got numbers here. And those numbers are the area to the right of the critical value. So there's no area to the left. It's all area to the right of the critical value, whether the critical value is on the left side or the right side. We need one on each in this particular case. We need one on the left and one on the right. And so to find the one on the right, we want to know what the area to the right of the right critical value is. And remember what's happened here. Alpha is 0.05. And half of alpha gets put out into each tail, and we need to find the critical values that give us that much area in that particular tail. So the test statistic on the right, the area to the right of the right test statistic, critical value is half of alpha, which is 0.025. So we're going to look for 0.025, and it's in this column. And then we're going to go down to the critical value row, and the critical value, remember, is sample size minus 1, which is 20 minus 1, which is 34.170. Okay, so that is the critical value on the right. Then for the left, the area to the left of the left critical value we know is half of alpha, 0.025, which means that the area to the right of the left critical value has to be 1 minus that. So 1 minus 0.025 is 0.975. So we're looking then for the critical value on the left. We're looking in the 0.975 column. And again, down at the, or in the 20 row, and the critical value on the left then becomes 9.591. So that's how you're going to use table A4 to find critical values for tests of standard deviation. Let's go back to the document. All right, so here's our critical value on the right, 34.170. Our critical value on the left, 9.591. And I put the mean on here just to show you. And by the way, when you're dealing with critical values, it's always a good idea to draw the sketch and mark the mean as a point of reference. And it is the degrees of freedom for a chi-squared distribution. So we mark the degrees of freedom in the middle here. And that tells us that which side is, what constitutes the left side, what constitutes the right side. So we've got our critical values marked. Now we need to know, is the test statistic, this 33.8, farther from the critical value on that side than, farther from the mean than the critical value on that side, and 33.8 is not bigger than 34.17, so it's not in the critical region, the area underneath the curve to the right of the critical value. It is smaller than 34.17, so it's just to the left of 34.17. Therefore, it is not in a rejection region, therefore it is not unlikely. And if we look at the p-value approach, we have to use the chi-squared CDF function. And CDF functions, we've seen these before in the test of proportion. There was a normal CDF. In the test of the mean, there is a t-CDF. And when we're dealing with tests of standard deviation, it's a chi-squared CDF. All these CDF functions are under second vars. And in this case, it is 8 if you have a TI-84 plus, or 7 if you have a TI-83 plus. There's a function on the TI-83 plus, or TI-84 plus, that is not on TI-83 plus, which means it is not down at 8. This one is not down at 8, it is at 7. And we saw in the previous videos for test of proportion and test of the mean that a CDF function requires a left bound and a right bound for the area farther from the mean than the observed test statistic, 33.8. Now, we have to realize, though, for tests of standard deviation, the chi-squared function doesn't have any negative values. It starts at 0, okay? It starts at 0. And therefore, if we're looking at, if the test statistic is on the left and we need to find the area to the left of the test statistic, well, that area doesn't start until 0, and then it comes up to the test statistic value. But our test statistic is on the right. So we would start at the test statistic. If we're on the right, we'll start at the test statistic and end at a very large positive number. Okay, so if you're looking on the left, you're going to start at 0 and come up to the test statistic. If you're looking on the right, you're going to start at the test statistic and go to a large positive value. Now, since this is a two-tailed test, we're going to find the area farther from the mean than the test statistic. And then we're going to double that to get the p-value. Once we find the area to the right, in this case, we have to double it to get the p-value. Okay? If we were on the left, if we found the area to the left, we would still have to double it to get the p-value. Only when you have a two-tailed test do you have to do that. Okay, and we saw that also in tests of proportion and tests of mean. So the area underneath the curve to the right of 33.8, the test statistic, is chi-squared CDF 33.8, comma, large positive number, comma, degrees of freedom, and then we end up with 0.0550. Okay, because we had to multiply that area. I'm sorry, we had to multiply that by 2 to get the 0.0550. Okay, so let's take a quick peek at the PDF function or CDF function. Let me clear this. And remember, it's second vars, and it is number 8. And we have to start at the test statistics since we're on the right, 33.8, comma, and then we go to a large positive number, 9999, and then we need to put in the degrees of freedom since chi-squared has a degrees of freedom, 20, sample size -1, and we hit enter and we get 0.0275. Then we would have to multiply that by 2. And that gives us 0.0550. Okay, let's stop this and go back to our document. And once we have the critical value information, comparing that to the test statistic and comparing the p-value to alpha, we see that the p-value is bigger than alpha, which means we fail to reject 8.0, the assumption. And the critical value was, the test statistic was closer to the mean, less than the critical value on the right, therefore not in the critical region, which would also cause us to fail to reject. And then we go to the flowchart handout, and we use that to determine what our statement of conclusion is. And let's just take a peek at what we would get here. Remember, this is a two-tailed test because alpha said sigma was equal to 10. So let's go find that. And we're going to have to scroll up to the 4th page in the formulas and tables handout. The first question, does the original claim include the condition of equality? Yes, it said equal. So we're over here. Did we reject 8.0? No, we did not. So we failed to reject. So we're down here. And the wording is, there is not sufficient evidence to warrant rejection of the claim that, and then we would say sigma is equal to 10. And that concludes then the first problem. And so let's go back to the document and look at the second problem. An aiming mechanism for a medical laser is required to have a standard deviation of the aim angle no more than 0.0250 degrees. A sample of 101 mechanism measurements yielded a standard deviation of 0.0277 degrees. Assume a 0.05 significance level and test the claim that the standard deviation is greater than 0.0250 degrees. I've highlighted in yellow the claim information, and I've highlighted in blue the sample information. So in the yellow area, I see we have a significance level of 0.05, so that defines alpha for us. And then the rest of it says test the claim. So here we have a claim that standard deviation is greater than 0.0250. So sigma is greater than 0.0250. The null hypothesis, which is our assumption, is always equal. And then since the original claim did not have equality in it, the alternate hypothesis is going to be the same as the claim. Then we go down to the test statistics, step 2, and we need sample size and sample standard deviation, which were given in the problem. Sample of 101, others are sample size, yielded a standard deviation of, there is our standard deviation value, 0.0277. And again, remember our chi-squared has a degrees of freedom, so that is going to be, in this case, 100. Substitute the numbers in, we get a test statistic value of 122.766. We want to know if this is unlikely or not unlikely. Looking at critical values, we have a right-tailed test since the relationship in H1 was greater than. Therefore, we need one critical value on the right, which splits all of the chi-squared test statistic values into those that are bigger than the critical value, which would cause it, which defines the critical region or rejection region, and those that are not, which is the not reject, fail to reject region, okay? Once we have that, well, let's see what it should be. We need to be looking in, our table requires that we know what the right tail area is, and it is all of alpha in this case for a right tail test, so it is 0.05. We'll be looking in the 0.05 column of that table, and the 100 degrees of freedom row, so let's see what we get in that location. Scroll down to the last table. All right, we're in the 0.05 column because the area to the right of in a right tail test is 0.05. And we'll scroll down to 100, and the 100 row is the last row, and 124.342 is the degrees of freedom. So let's go back and look at what we got here, 124.342. And then we plot the test statistic, which is 122.766, to determine if it is farther from the mean, farther from 100 than 124.342, and it is not. It is less than 124.342. Therefore, it is not in the critical or rejection region. Therefore, it is not considered unlikely. And then let's look at the p-value approach. What we're going to do then is plot the p-value and find the area underneath the curve farther from the mean, or plot the test statistic, find the area underneath the curve farther from the mean than the test statistic. So we want to find the area underneath the curve starting at the test statistic, since it's on the right, start at 122.766 and go to a large positive number using the chi-squared CDF function. Let's go ahead and put this in a calculator. Share, let me clear what we got here. Second, vars, number 8. And we'll start at the test statistic, which was, all right, 122.766. and comma, and we'll go to a large positive number, comma, and 100 degrees of freedom. Start over again. Second, vars number 8, 122.766. Oh, come on back. If I could handle a mouse, that would be dangerous. Comma, large positive number, comma, and 100 degrees of freedom, and hit enter. And we get 0.0608. Okay, let's stop sharing this. Go back to the document. And we've got our test statistic. I'm sorry, we've got our p-value. We've got our critical value up above here. Compared to the test statistic, it was less than the test statistic on the right. Therefore, it was not in the critical region. This is in our step 4. The p-value was bigger than alpha, so we would fail to reject. And the test statistic was not in the critical region on the right, therefore we failed to reject. And then we would go to the table, the flow chart in the formulas and tables handout. It was not rejected, and the claim was right tail, so there's not sufficient sample evidence to support the claim that sigma is greater than 0.0250 degrees, repeating the claim in the statement of conclusion. And let's go to the third problem. A plexiglass manufacturer routinely checks the precision of the thickness of their plexiglass panes. Their requirement is that their pane thickness has a standard deviation of no more than 0.06 millimeters. The thickness has a normal distribution. A random sample of 31 panes was found to have a standard deviation of 0.045 millimeters. Test a claim at the 0.05 level that their standard deviation is less than 0.06. So there is the claim. And that information is highlighted in yellow. We got alpha is 0.05, and the claim is standard deviation is less than 0.06. So alpha is 0.05, and standard deviation sigma is less than 0.06 is the claim. Again, H0, which is the assumed value of the parameter, is always equal. And the alternate hypothesis, since the claim did not include equality, the alternate hypothesis is the same as the claim. And then we go down to the test statistic calculation in step 2. We substitute the numbers in. And remember what we found up here, sample was 31. Sample size is 31, and the sample standard deviation is 0.045. So we substitute that information in, and we get a test statistic value of 16.875, and we want to know if that test statistic value is unlikely or not unlikely. So using the critical value approach, we would go to the table, and this time we need a critical value on the left. So the area to the left of the critical value is going to be all of alpha, 0.05. The area to the right must be 1 minus that, or 0.95. So we would look in the 0.95 column. So let's just do that. We look in the 0.95 column, and we're looking in the 30 row because our degrees of freedom was 30, and we get 18.493. So if we go back to our document, 18.493 is a critical value. Then we plot, and in our critical value sketch, notice we put the mean in the middle. 30 was the mean. That gives us a point of reference. 18.493 is to this side of 30. And then we plot the test statistic relative to that, and we see that it is less than 18.493, which means it's to the left. And in a left-tailed test, that means it's in the critical or rejection region. So that says that 16.875 is unlikely. Then we go to the p-value approach and look at finding the p-value. Remember, we want the, excuse me, the area underneath the curve farther from the mean than the test statistic. So since it's to the left of the mean, we want the area to the left of the test statistic, which means it starts at 0, since the chi-squared distribution starts at 0, and comes up to 16.875. So our chi-squared CDF is going to look like this. Second bars, number 8. And we're starting at 0 on the left, coming up to the test statistic, which was 16.875. And then we're going to put in the degrees of freedom, which in this case was 30. And hit enter. And we get 0.025, well, actually 60, 0.0260 to 4 decimal places. Since this is a 5, that becomes a 10. We carry the 1, so that's a 0 there. This becomes a 6. 0260. All right, so we'll stop sharing and we'll go back to the document, and we then get, we got our test statistic, or we got our test statistic and critical value above there. We decided that the test statistic was in the critical region, and we compare the p-value to alpha. It is less than alpha, therefore we will reject H0. In both cases, we were rejecting H0. And we state our conclusion, go to the flow chart. The original claim did not include equality, so we go down that first arrow. Then we answer the question, did we reject or fail to reject? And we say we rejected, so we go to the right and we say there's sufficient evidence to support the claim that, and we repeat the original claim, that sigma is less than 0.06, in this case, millimeters. Okay, now we've got a couple of short ones here. These are tests where they're not complete hypothesis tests as we've done before. They are partial hypothesis tests in the sense that we've got all the information in the problem to describe the claim, and we have the test statistic already calculated for us, and either a p-value or a critical value already given to us. So we've got everything we need through through step 3. We just have to complete the hypothesis test by doing step 4 and step 5. So we have to make our decision and state our conclusion. So let's look at what the first one gives us. A cereal company uses automated processes to fill their 18-ounce Sugar Max cereal boxes with 18 ounces of cereal. A company wants the standard deviation of the amount of cereal in boxes to be less than 0.5 ounces. The hypothesis test of the claim that the standard deviation is less than 0.5 was conducted at the 0.05 significance level. Now, don't confuse the significance level of 0.05, 0.05, with the value in H0 of 0.5, okay? So we've got an assumed value of sigma as 0.5, but we've got a significance level of 0.05. All right, 101 boxes of cereal were tested and a test statistic value of 81 was observed. The critical value for this test was found to be 77.929. Okay, that's everything through step 3. We've got a claim, sigma is less than 0.5. Okay, we've got a test statistic, which is 81. And we've got a critical value of 77.929. Well, since the claim is less than, that means H1 is also less than the alternate hypothesis, which makes it a left-tailed test. And we got a test statistic of 81 and a critical value of 77.929. We draw a little sketch starting at 0. And we plot the test, well, the mean would be at 100, which is up in here. And we plot the critical value of 77.929, and we want to know where the test statistic of 81 is. Well, since we're on the left, we're going from 0 up to 77.929, and then we go a little farther to get to 81. So it is not in the critical or rejection region, okay? It is bigger than 77.929 on the right, okay? So that means that the test statistic value is not unlikely, okay? 81 is greater than, test statistic is not farther from the mean than a critical value. We should have failed to reject H0, okay? This answer is wrong. I need to fix that. So next time you see or read, you'll see in the content of your D2L homepage, I'm going to put a new version of this up with this correction in it. You should basically, if you've already printed this out, just write in fail to reject. Then we state our conclusion using the flow chart. Claims not include equality. H0 was not rejected. There is not sufficient sample. All right, I just didn't type it in right up here. The H0 was not rejected, so we failed to reject. There's not sufficient sample evidence to support the claim that sigma is less than 0.5. Okay, so there's one little mistake to correct. All right, let's look at the last problem. Westinghouse at one time was in competition to provide electricity to homes. At the alpha equals 0.05 significance level, an independent tester tests a claim that the standard deviation of the length of time to wire a 2-bedroom home was 1.2 days. A sample of 31 homes yielded a standard deviation of 1.37 days. The p-value was found to be 0.2470, and the test statistic was found to be 39.102. State the decision and state the appropriate conclusion as related to the original claim. So we've got everything through step 3. We've got a claim, and the claim was a standard deviation was 1.2 days, making it a two-tailed test, okay? We got a p-value, 0.2470. Well, do we need the test statistic? No, because p-value, we can make our decision with the p-value and alpha. Alpha is 0.05. We need those two pieces of information. And so we would say in our step 4, 0.2470 is greater than 0.05. Therefore, it's greater than the significance level. We will fail to reject H0. And notice this was a two-tailed test, but we don't have to worry about that because the p-value was given to us. It's already been we went through the process of finding it on one side and multiplying by 2. That's already been done. So we fail to reject H0, and then we go to the flow chart. The claim includes equality, so we got to go to the right on that after the first question. and H0 is not rejected, so we was rejected. So again, here's an error. I'm sorry, it was not rejected. And so we go down. So we're in that second set of words. There is not sufficient sample evidence to warrant rejection of the claim that sigma is equal to 1.2. And so you're liable to see, or you will see kinds of problems where they are partial hypothesis tests, where information is given through step 3, and all you need to do is finish the problem by stating making a decision and stating a conclusion. So this should complete tests of standard deviation.